in this review, we're going to cover differential equations in a way that's going to help us understand the Schrodinger wave equation, which is at the heart of quantum mechanics and is in fact a differential equation itself. So a differential equation is when you have a function, you take the derivative of that function and it's equal to the function itself. So for example, here I have a couple ones. So here we have dy dx, so the derivative of y with respect to x is equal to a y. So it's the derivative of y is equal to the original function y itself. And another common example we'll encounter here is when you take the second derivative of y with respect to x and get some constant times y. And so these are the two examples that we'll focus on in this review, and I'll mention others here in a little bit. So one common physical example of a differential equation that you may have encountered in physics is the motion of a spring. So the force that's stored in a spring as you extend it is equal to negative kx, where x is the displacement and k is this spring constant. So that's well and good. And we know from Newton's second law that the force of anything is equal to the mass times the acceleration. Now, acceleration is, of course, two derivatives of position with respect to time. So that's equal to mass times d2x dt2. So now you can see the differential equation aspect coming in here. So I'll do some rearranging here, and we get that the second derivative of the position with respect to time is equal to negative km times the position. So here we have an example of a differential equation, like this one we have above. And this differential equation, the fact that the motion of a spring is described by this differential equation, gives rise to the fact that we see this oscillating motion of a spring, right? If you have a spring, it extends and contracts and extends and contracts. And we'll see how that bears out over the course of the semester and a little bit in this review as well. So in this review, like I mentioned, we're just going to focus on these two types of differential equations I've listed up here. There are, of course, many others, some of which we will use over the course of the semester, where the solutions will just be supplied to you. And so in most cases, these solutions were known by mathematicians way before quantum mechanics ever became a thing. And there are, of course, other differential equations that are not solvable, that will need computers, or not we in the class, but that scientists need computers to solve in order to get reasonable approximations. So here we'll just focus again on these two. So the first example is if we have a derivative of some function y with respect to x, and that's returning us the same function multiplied by a constant. So if you want, you can go ahead and pause the video here and think about what kind of function would fit this differential equation. And the kind of function that would is, of course, an exponential function. So if we have some function, so say y is equal to e to the ax, and we take the derivative of this function with respect to y, we're going to bring down that coefficient in the exponent. So we have a e to the ax, which is just equal to a times y, which is what a differential equation is giving us. Now, the second type of differential equation we'll see is that, and we'll want to be able to solve, is the second derivative here. So we take two derivatives of y, and that gives us, with respect to x, and equaling again ay. So if you're following along well, you could say, well, that's pretty darn easy. All we need for y is to be e to the square root of a times x, right? That's just some constant. If a was 4, the square root of a would be 2. So then we take the derivative of y with respect to x, and that gives us the square root of a times e square root of ax. We take another derivative, and that's going to give us square root of a squared, right, which is a, times e to the square root of ax, which is just ay again. Boom, we're done. Now there's a problem with that, and the main problem can be seen up here, right? So in a lot of cases, our constant is going to be negative. So that will work totally fine. So for example, if our negative was here in this first function, that's totally fine. It all works out, and we can just do one derivative. The exponential works perfectly if we're just taking one derivative. However, if we're taking two, right, there's no real number that you can square to get a negative number. And so that's going to harken back to our last review, and our answers here should be imaginary. So if we were just to plug that in here, right, so if we had y is equal to e to the I times the square root of a x, we take one derivative of this, we end up with I square root of a times e to the I square root of a x. We take a second derivative, and that gives us I squared, which is -1, square root of a squared, which is a, so it gives us negative a times e to the I square root of a x, which is negative a y. So here, if we have an imaginary solution, that works out. Now, if we remember the last review, if we have e to the I x, right, we can use Euler's formula to reconstruct that in terms of sine and cosine. So this function here, this y, is also equal to cosine square root of ax plus I sine square root of ax. And it's the same solution. And I encourage you to plug in cosine and sine and take two derivatives and see if we end up with the negative a times y. And we should. And so in general, when we have two derivatives, so the derivative here, so two derivatives of y with respect to x, a good solution for that is the sum of trigonometric functions, so the sums of sines and cosines, and that can give us our solution. And in fact, if we go back to our spring example up here, the motion of a spring is best described by a trigonometric function. And you can see that's going to be a function that gives us this back and forth motion, right? It starts to look like a sine curve. And so that's all that we really want to know for this class about differential equations, to be familiar with these couple examples here, and as well to understand exactly where they're coming from. And again, we'll see more of this as we go on with the class and we actually get Schrodinger's wave equation and begin to work with that.